In this lesson, we're going to talk very quickly about the concept of function notation, and then we're going to take a look at the concepts of evaluating functions as well as the composition of functions. Your big idea here is still the concept of a function, and it's important that you walk away from this lesson recalling that a relation is a set of pairs of input and output values, and that a pairing of items from two sets is special when items from one set pair with exactly one item from the second set. So that's linked back to the concept of a function, which is a very special type of relation where each element in the domain is paired with exactly one value in the range. It's also important that you understand that functions can be added, subtracted, multiplied, and divided based on how these operations are performed for real numbers. One difference, however, is that the domain of each function must be considered. So let's take a look at function notation to start, and we want to highlight here what the difference is between a y equals and function notation. So if you look on the screen, what you see is y equals mx plus b. And that's the slope-intercept form of a linear equation, which we just spent some time talking about in our overview of linear functions. So y equals mx plus b should be something that you recognize. To the right, you see f of x equals mx plus b. Well, what's the difference? Basically, a function rule is an equation that represents an output value of an input value, but as far as we're concerned, there's not really a huge difference between the two representations. Really, the one on the right is kind of being a little bit more specific, and it's telling you right away that it is a function. So not a huge difference there that you need to be worried about. Function notation, this f parenthesis x, that's read f of x. That's how you're going to say that, or how you would write that out using words. Let's look at the different parts. The f here, that's the name of the function, and we're going to see examples throughout the course of this lesson where that letter changes. So sometimes we use f for g or h. I could use a of x or s of x, really whatever we want to name the function. X here, all right, inside the parentheses, that stands for an input value. We talked in our function basics lesson about the fact that the domain or the x values were the input values for a relation. F of x overall is the output value, and if you thought about this as an ordered pair, that would be the y value. So you put in an x value, you get a y value back, kind of like dependent and independent variables. The x goes in, and it affects the outcome of the dependent variable, which would be the y. So after that summary, let's talk now about the idea of evaluating functions. Basically, you're going to be given a function rule or function rules, and what we're going to do is say, for this given input, what's the output? This process involves substituting the input into the function and simplifying. So for example, given f of x equals 2x plus 1, we want to find f of 3. What we're going to do is take this input value, which is the 3, and we're going to put it in for the x in the function. We'll simplify. 2 times 3 is 6. 6 plus 1 is 7. So what we're saying is that the value of the function at 3 equals 7. 3 was my input, 7 is my output. I could think about this as a graph, and on the graph, this would be the ordered pair 3, 7. The idea of the name of the function becomes more important when we are talking about multiple functions at once. So in this series of examples, you're given an f of x, a g of x, and an h of x. It's really important that you look at the problem that you're being asked to solve. So for example here, we're being asked to find h of negative 3. If the name of the function is h, that means I have to use the h function to evaluate it. So here, if I'm asked to find h of negative 3, the first thing I'll do is write down the h function. H of x equals x squared minus 4. Take the input of negative 3 and substitute it for x. And now simplify using your order of operations. Negative 3 squared is negative 3 times negative 3, which is positive 9. 9 minus 4 is 5. So h of negative 3 is 5. What about f of 5? The name of this function is f, so we're going to get the f function. We see that f of x is 1/2 x minus 3. I'll take the input of 5 and substitute it for x. So we have 5 halves minus 3, which would be negative 1/2. So f of 5 is negative 1/2. I recommend that you pause the video at this point and try the last one on your own. Okay, the last example here, we're being asked to find g of negative 5. Our g function was g of x equals the absolute value of x plus 1. Substitute the input of negative 5 plus 1. Inside the absolute value would be negative 4. The absolute value of negative 4 is 4. So g of negative 5 is 4. Composition of functions, basically what this does is it combines two or more functions. And I like to think of this in terms of a manufacturing example. Basically what we do is we put some kind of an input here into a machine. So the input goes in here. Maybe that's raw aluminum that we take out of the earth, and the machine that we put it into rolls it into flat aluminum sheets. Those flat aluminum sheets come out of the machine here, but they would go to another machine, and those flat aluminum sheets maybe are rolled into soda cans. Those soda cans would come out the other side of the machine. So basically, composition of functions is about taking an input and performing actions on it and getting an output, and then using that output as the input for a new machine. So for example here, we're given f of x equals 3x plus 2 and g of x equals x squared minus 1. We want to find g of f of 3. So what we're going to do is we start here and we find the f of 3 first. Well, f of 3 would require us to use f of x, which is 3x plus 2. Substitute the input of 3, and we find that f of 3 is 11. Now what we're going to be asked to do is to actually find g of 11. What's happened here is the output of this first step has become the input of the next step. To do this, we have to use the g of x function, which is x squared minus 1. Substitute that input, and we find that g of 11 is 120. Putting the answer together, g of f of 3, when we evaluate that composition of functions, would be 120. It's important now that we discuss some alternative notation. This first example of composition of functions was presented using what we call nested parentheses. Alternative notation includes this open circle, but they mean the same thing and they would be read the same way. So this still reads g of f of 3. So let's look at a few more examples. We are going to do that g of f of 3 problem. So let's take a look. Here this one is presented with that open circle. We're still going to start here. We're starting with that number that's closest, or sorry, with the letter that's closest to the number. So starting with f of 3, that means we need the f of x function. So f of x is 1/2 x minus 3. Substituting that input, we get 3/2 minus 3, which is going to be negative 3/2. So f of 3 equals negative 3/2. The next one out is g. We're going to be asked to find g of negative 3/2. We use the g of x function, so g of x equals the absolute value of x plus 1. Substitute, we get the absolute value of negative 3/2 plus 1, which would be the absolute value of negative 1/2. which is 1/2. So g of negative 3/2 equals 1/2. Putting the answer all together means that g of f of 3 is 1/2. I recommend that you pause the video here and try the next example on your own. Okay, hopefully when you evaluated g of negative 2, you picked that g of x function, and you ended up evaluating the absolute value of negative 2 plus 1, which should have given you 1. So g of negative 2 equals 1. Take that 1 now and put it into the h function. H of x was x squared minus 4. So negative 1 squared minus 4. I'm sorry, positive 1 minus squared minus 4. So 1 minus 4, which is negative 3. So hopefully you found that h of g of negative 2 was negative 3. The next example looks harder, but really what it requires is just a third step. So let's take a look at this next example. We want to first find g of 1. Well, g of 1 would be found by doing the absolute value of 1 plus 1, which is the absolute value of 2, which is 2. Next we move out to the h function, so we're going to find h of 2. That output from the g becomes the input for the h. So that would be 2 squared minus 4, so 4 minus 4, which is 0. Finally, now we're going to take this output from the h and put it into f, and we're going to find f of 0, so 1/2 times 0 minus 3, which is negative 3. So f of h of g of 1 would be negative 3. All the examples that we've looked at previously have included algebraic representations of functions. We can also evaluate functions using graphical representations, and that's what we're going to look at here. You are presented here with a graph, and this is the graph of the function f. In example number 9, we are asked to find f of 2. So what's important that we recognize here is that the input is 2. That means that x is 2. So what we want to do is we want to go to 2 on the x-axis, which would be right here, and go to where we intersect the graph of the function. Slide across to the y-axis, and we see that we're at negative 2. That output value of negative 2 corresponds with the input value of 2 for this particular graph. So for this graph, we say that f of 2 equals negative 2. The composition of functions is going to work in a very similar way. Start with f of 3. So we come to 3 on the x-axis, down to the graph, and across, where we're at negative 1. So the value here was negative 1. Now we find f of negative 1. Start here, come down to the graph, and across, and we're at negative 3. So f of 3 equals negative 3. So you can see here that it's possible to evaluate functions and also evaluate the composition of functions using a graphical representation.